Welcome to eXtension's webinar hosted by the UAS Learning Network. My name is James Robbins, and I am a professor at the University of Arkansas System Division of Agriculture. In this session, I would like to briefly describe how we used UAS for a specific plant production issue. The research problem that we applied a UAS to was the counting of plants in open field nurseries. Historically, this process is time-consuming, expensive, most likely conducted using manual methods, and in very large nurseries, sampling techniques will be used to estimate a crop's overall count. This research project is a classic example of how we might try to solve the problem using a ground-based approach. Starting in 2009, with the help of Dr. Reza Asani at the University of Florida, the team evaluated a ground-based solution to the research problem. However, for a variety of reasons, we shifted our approach to the sky. The research team was an early adopter of UAS dating back to May of 2010. Again, it is important to note that a UAS is nothing more than a platform for sensors that you already use. A UAS simply gives a different perspective and offers advantages and disadvantages. First, let's highlight the UAS that we typically used. Our UAS was an 8-bladed rotary aircraft, or octocopter. Most of our UAS was based on a kit purchased from Microcopter in Germany and built by Dr. Joe Maha, now at Clemson University. As shown, the components cost about $4,500. The weight of the frame and one LiPo battery is 2.2 kilograms. Flight software used is provided by Microcopter. We will spend a minute to briefly describe how we use a UAS in our research. Again, our research problem is trying to develop an automated method to count plants on the ground in open field situations. For most of our research, we construct nursery beds for different treatments. For example, in this photograph, we are evaluating the effect of plant spacing on counting results. In this example, we established a flight path using the software and flew the octocopter in an S pattern as shown by the pink line over the research blocks. We were also interested in the effect of image resolution on counting performance, so we flew the aircraft at different altitudes over the research blocks. For most of our research, we use a digital camera. We won't discuss in detail here, but we then process the images using image-based analysis software. This table is an example of our counting results. Many of you would benefit from our years of experience and mistakes. Here are some unexpected issues that arose. In the fall of 2013, Earth experienced an 11-year peak in solar flare activity that could interfere with our GPS-based flight navigation. Based on discussion groups, we decided to limit flights to days with low activity, which greatly impacted our planned flights. Second, we were disappointed in the useful life of our current LiPo batteries. Thirdly, because we were required to be legal, we found that the process to get and maintain a Certificate of Authorization, or COA, from the FAA was an incredibly burdensome process. And lastly, we still lack a clear understanding of the impact of wind speed on our results. This subject, like others we discovered, offer research areas for the future. At this time, I would like to acknowledge those that contributed significantly to this research effort. I previously mentioned Dr. Reza Asani at the University of Florida. Dr. Dharmendra Saraswat, now at Purdue, was a critical participant. Dr. Joe Maha, currently with Clemson University, contributed a great deal to this project, and Josue Leyva was my master's student that worked specifically on this project. I appreciate this opportunity to share our research using a UAS with you.